here where we instead of x we am I audible now? Sorry, I have to ask you again and again because we found some network issue today. Uh, Instead of x, we have written here input. So f of input, what it is? 2 into input plus 3. And what g of input will be? Input square. Now what g of g composite f of x is equal to g of f of x. It will be there. Okay. Here we are considering this one, this order. G composite f means what? G of f of x. So what this will be? G of f of x means instead whatever the f of x will be there, that we will write, and g of f of x means whatever the g function will be there, that we will apply on f of x. So g composite f of x, that is g of f of x, will be 2x plus 3 square. Okay, what is that? Square. Whatever the input is there, square. That square is the g function. What the input here is? F of x. So f of x, what it is? 2x plus 3. And what its function, it is square. Okay, so g composite f of x, it will be 2x plus 3 square. Then what if we reverse the order of f and g? It will be f composite g of x is equal to f of g of x. Now what g of x is? It's simply the x square. Okay, g of x is x square. So when we apply g, then first we apply g and then we apply f. So g function is applied to f function and it gives us 2x square plus 3. Instead of x, we will write only the x square because simply the g function is like that, x square. Okay, g of x is x square, and if we apply f to x square, what it becomes is 2x square plus 3. Okay, so what we can take it as g of f of x is not equal to f of g of x. Always it will be a different one. Then what the properties which are possessed by this composition of functions are? The composition of functions is always associative. Okay, composition of functions is always associative. Then means what it is? The composition of functions is always associative. A property inherited from the composition of relations. Okay, same is the property that is possessed by composition of relations also. What it is? F, G and H are composable, then F composite G composite H is equal to F composite G composite H. Okay, what the function, what the property is? F, G, H, F, G and H are composable, then what it is? First we composite G and H, and then result of G composite H is composed with this F, is giving the same result. Like here, if we compose f and g functions first, and composition of these functions is composed with h at the last. Okay, these two sides are equal. LHS is equal to RHS is there. So what we are going to say is the composition of functions is always associative. Next property is the functions g and f are said to commute with each other. Are said to commute with each other if g composite f is equal to f composite g. Okay, we actually have seen now only that g composite f is not equal to f composite g, but some uh, special cases are there where this commutativity is possessed. Commutativity is a special property. It is a special. It's not always true, but sometimes it is true. Attained only by particular functions and often in special circumstances. Okay. It is attained only by particular functions. Not all functions possess this commutativity. Only under special circumstances some particular functions possess this commutativity. Okay, the composition of one-to-one injective functions is always one-to-one. Similarly, the composition of onto functions is always onto. Okay, here we have seen in the example. Here we can see here all the functions are one-to-one functions. This is not a onto function, only one-to-one function is there. So composition of these two functions is one-to-one. Okay, onto, it's not onto, but in case of onto functions compositions, the result is onto function, and in case of one-to-one, the result is one-to-one. Then next term we are going to see is the inverse of function. What inverse of a function is? The inverse function of a function f is called inverse of f is a function f inverse. Here we can see how it is written like this one, f inverse, that undoes the operation of f. Whatever the operation is performed by function f, that is undone. Okay, f inverse undoes that operation f. It it performs exactly opposite function of f, so it is known as inverse. Whatever the function f has done, it performs the reverse process of that. Means whatever the function f has done, it undoes all those activities. Okay, the inverse of f exists if and only if it is bijective, and if it exists, it is denoted by, for a function f from x to y, its inverse is f inverse from y to x. Okay, when the inverse exists, if the function is bijective. Bijective means what? One-to-one and onto function at a time. If the function is bijective, that is one-to-one and onto at a time, then only its inverse exists. And if f is from x to y, f inverse is from y to x. It admits an explicit description. It sends each element x belongs to x to the unique element y belongs to y, such that f of x equal to y. Now, as we are dealing with functions, this is the case most of the times, f of x equal to y. We can say always, not most of the times, always. The meaning is like this, f of x equal to y, where small x is the element of this set x and small y is the element of set y. As an example, consider the real valued function of a real variable given by f of x equal to 5x minus 7. One can think of f as a function which multiplies its input by 5 and then subtracts 7 from the result. To undo this, one adds 7 to the input and then divides the result by 5. What this f of x is? 5x minus 7 means multiplied, input is multiplied by 5 and 7 is subtracted. What the inverse function will be? Yes, the reverse function will be 7 will be added to the input, as here it is subtracted. 7 will be added to the input and the result will be divided by 5. Okay. Therefore, the inverse of f is the function f inverse from R to R, defined by f inverse of y is equal to y plus 7 divided by 5. Okay, what it is? Y plus 7 divided by 5. By interchanging the roles of the independent and dependent variables in a given function, one can obtain an inverse function. Okay, by interchanging the roles of independent and am I audible now? By interchanging the roles of the independent and dependent variables in a given function, one can obtain an inverse function. Inverse functions do what their name implies. They undo the action of a function to return a variable to its original state. Thus, if for a given function f of x, there exists a function g of y such that g of f of x equal to x and f of g of y equal to y, then g is called the inverse function of f and given the notation f inverse. Okay, the notation given is f inverse, whereby convention the variables are interchanged. For example, the function f of x equal to 2x has the inverse function f inverse of x equal to x by 2. Okay, inverse function concept is like this. Inverse functions do their name implies. What their name implies, they undo the action of function to return a variable to its original state. It will inverse the function f of x and will give the value x. Okay, like that. Here we can see the diagram, like a is here it is one-to-one and onto function. You can see it is a bijective one. Here a is assigned to 3, b is assigned to 1 and c is assigned to 2. What the f inverse will be? 1, 2, 3 at the first as the first set and abc as the second. Here a is assigned to 3, so here 3 is assigned to a. Here b is assigned to 1, so here 1 is assigned to b. And here c is assigned to 2, here 2 is assigned to c. It is simply the inverse of functions. Let f be a function whose domain is the set x and whose codomain is the set y. Okay, means f is the function from x to y. Then f is invertible if there exists a function g from y to x such that g of f of x equal to x for all x and f of g of y equal to y for all y. Okay, inverting the function, it is giving the original values. Okay, the f is invertible, the function f is invertible, then there is exactly one function g satisfying this property. The function g is called the inverse of f and is usually denoted as f inverse. Okay, if f is invertible, okay, means f inverse exists there, then there is exactly one function g satisfying this property, means f inverse is equal to g, means unique yeah, unique inverse will be there. Okay, means for f there exists g satisfying the property. G here is denoting f inverse. Okay, the function g is called as inverse of f and is usually denoted by f inverse, like this here we can see.